Let's go ahead and get started with analyzing natural response of parallel RLC. As I said, I'm going to start with this and then, well, the other three combinations, natural step response of parallel RLC, natural response of series RLC, and step response of series RLC. I'm going to discuss those later. Let's start with this one. Let's say that I have a circuit that looks like this. So I have a C, an L, and an R that are in parallel, and there's no source connected to them, so it's a natural response. Of course, the source could have been connected. So this is the circuit, and this is how the circuit looks like after the switching, right? So after the switching, it was probably before the switching, it was probably connected to a bunch of sources. So I have some energy stored in the capacitor and the inductor. And the moment I have connected or disconnected the switch, after I have made the switching so that there is no source connected to this circuit, it's going to look like something like this, right? So I can imagine that capacitor and inductor could have, so and or inductor, so like both of them or one of them could have some energy stored in them. Or some initial energy stored in them. Therefore, let's say that if I want to actually say the initial voltage in the capacitor, so V capacitor, VC, initial, I'm going to call that a V naught, let's say. And IL initial, I'm going to call that I naught. Okay, so because there's some energy stored in the capacitor, I can imagine that there is some initial voltage in the capacitor, and it's shown as this. So there's a V naught, the initial voltage on the capacitor, and there's an I naught, which is the initial current on the inductor. So I have some initial values, but what I want to know is that, well, I want to know every voltage and current in this circuit, right? So I need to actually write some KCLs and KVLs to figure that out, right? That's what I did with the RL circuits and RC circuits. I started with writing a KVL or a KCL, and then I got to some sort of a differential equation. I solved that, and I found my voltages and currents. Now here, because it's a parallel circuit, I know that one thing that is common between these three elements is the voltage across them, right? So the voltage across R, the voltage across L, and the voltage across C are the same thing because, well, this node, and this node, they're the same node, and similarly, this and this and this points are actually the same node, okay? So all of them have a V across them. So let's actually write everything based on that and then solve for V. Once I have V, then I can easily find the current in each inductor. That's the voltage across all the elements. And then once I have it, I'm going to have the current flowing through each element, because for resistor, it's just going to be that V divided by R. For capacitor, it's going to be C dV over dt. So I just have to take the derivative of that voltage expression and multiply it by C. For the inductor, I have to do the integral, right? But when I have V, I'm done, right? I'm done in terms of circuit analysis. I just need to do some math to find everything else, okay? So let's write KCL. So if I write KCL, I'm going to get this. So what are these things? So the first one is, the first term here is really the current of the resistor, V divided by R. The second term, let's use a different color, here is the current of the inductor, right? So this is IL. I know that VL, voltage of an inductor, is L dIL over dt, right? This is by definition. So IL is going to be the integration of the voltage plus the initial current flowing through the inductor that we defined before, right? And the last one is current of the capacitor, which is C dV over dt, right? So I know that since I've defined all of them leaving the node that is indicated in red, I know that addition of them, the sum of them is going to be 0. Okay. Now, from this point, I can actually take the derivative of all the sides. So basically, if I take the derivative of basically all the terms on both sides with respect to basically time, this v becomes dv over dt, right? And I get the 1 over r still there. The integral is going to go away because derivative of an integral is just going to be, well, they cancel each other. So I'm going to get the v and then the 1 over L. So that's coming from there. The derivative of I naught, which is basically a constant initial current of the inductor, is just going to be 0. It's a constant, so its derivative is with respect to time is going to be 0. And dv over dt, because I took the derivative of it again, it's going to be a second derivative. So it's going to be d2v over dt2. And c is going to stay there, right? Now I have to actually move things around a little bit. So I'm going to divide to keep the second order derivative without it, with the coefficient 1. I divide everything by c. So if I do that, I just bring this term to here. dv over dt is going to be 1 over r divided by c, so 1 over rc, so that's going to come here. And then v over L, it's going to be v over L divided by c, right? So this is basically divide by c. And from here to here, I'm doing a d over dt of the both sides, okay? Then I get to this characteristics kind of equation, the differential equation that it's kind of cleaned up. Now I have to actually solve this differential equation, right? So if I solve this differential equation, the expression that I get for v is going to be the answer that I'm going to have. So from this point forward, it's just going to be math. So if I want to solve this differential equation, first of all, I cannot solve it the way I did it for the first order differential equations in chapter 7. I cannot just basically do separate the derivative elements and basically do the integration over dv and over dt on the two sides because, well, it's a second order. So how do I solve this? Well, ideally, you have some background knowledge on differential equations, so you would know exactly how to solve this. But from my experience from previous years, a good number of students in the class don't have that background because you haven't taken any courses on differential equations. But I don't want to actually tell you that this is the answer accepted from me without any kind of explanation. So I try to actually explain to you how we get to this expression for v. How do we solve this differential equation in a more kind of like an intuitive way? Okay. So how do I go about this? Well, I make an observation. I look at this equation and I see that I have the second derivative of a function, my function being v, right? V is a function of time, right? So the second derivative of the function plus some constant times the first derivative plus another constant times the function itself is 0, right? So I need a function that its derivative and the second derivative, then I add them by some sort of basically after multiplying those terms with some random coefficients, I can always get 0, right? If you think about it, this means that the function, its derivative, and its second derivative should be of the same nature. What do I mean by that? Just imagine if I had the function as a sine function, right? It could be like basically, it doesn't have to be sine of t. It could be like basically have some coefficient, let's say, I don't know, 5 sine of 2t, right? Doesn't have to be a plain simple sine of t. You could have some random coefficients here, but if it's of the sine nature, its derivative is going to be cosine, right? And the second derivative is going to go back to sine, right? Derivative of a sine is cosine, cosine's derivative is sine. So there is no way that I can actually set these coefficients that no matter what is the coefficient, I would get 0 out of this equation for all times. Remember, this should work for all times. I can actually, for a certain value of t, I might actually make sure that, like, well, I don't know, 5 sine of t plus or minus 7 cosine of t plus 5 sine of t becomes 0, right? At the specific t, I could actually achieve that. But then if I want this to actually work for all time, then because sine and cosine are not of the same nature, they're not the same function, I cannot actually make that happen. If all these three terms were sine, then I could just set the coefficients in a way that it doesn't matter what is the time. Basically, at all times, basically, if I had sine, sine, and sine, then all I need to make sure was that the coefficient of these three, when I add them up, is equal to 0. Like, for example, I have a 5 here, a 2 here, and a -7 here, right? They just add up to 0. It doesn't matter what is the time, right? Sine of t could be anything. Because I'm multiplying with the coefficient 0, I'm going to get a 0. But then, because sine's derivative is cosine and the second derivative is again sine, there's no way that I can actually guarantee that. I cannot do that with polynomials as well, right? Imagine if I had x2 or like 2, or let's make it 3x2 minus 2x, right? What would have been the derivative? It would have been 6x minus 2. And the second derivative would have been 6, right? Again, I could choose these numbers, 3, 2, 6, and well, the 6 is actually calculated. I could choose these coefficients any way that I want, but at the end of the day, I could cancel all the terms that had an x. Sorry, it should have been t, like it's a function of time. So let me actually write it as a function of time. So 3t squared minus 2t, then it would be 6t minus 2, and then 6. So I could choose these coefficients in a way that all the terms that have a t cancel out with each other, all the constants cancel out with each other, but there's nothing I can do about the biggest term, right? And it doesn't matter if I go with the squared or like, I don't know, t to the power of 17 or t to the power of 32 or whatever, right? A polynomial is not going to work because I cannot make it happen. Like, I cannot guarantee that it's always 0 for all times, because there's always a term that does not appear in the derivative and the second derivative. So what is the function that I know that its derivative and the second derivative are of the same nature? Well, e to the power of t. I know that the derivative of this is going to be also e to the power of t, and the second derivative is going to be also e to the power of t, right? Of course, it's not going to be simply e to the power of t. I'm going to need some, like, basically some k constant, and then some, I don't know, let's call the constant behind it a, and this constant s, right? I'm going to need some constant. Let's write them in a different color. So e to the power of t, and then I do need an a and an s here, right? And then, well, this is going to be basically a s e to the power of st, and then this is going to be again a s squared e to the power of st, right? All I need to do, since all of these terms are e to the power of st, all I need to do is to choose a and s in a smart way so that they cancel out. For example, if I choose a or s negative, then this term would be negative, and then the other one would be positive. I just need to actually choose the values right. So there is a way to actually get this to become equal to 0, right? This is why I would know that for this differential equation, the answer v should be something like a constant, e to the power of s times t, right? So s is a constant, a is also a constant, right? So I'm going to plug this into the equation in the next slide and see what will happen. So we started with this circuit, we wrote the KCL, we got to this equation, and then in the previous slide, we realized that the V should have, the answer to this equation should have this form, where A and S are constants that I have to find, right? That basically, for this circuit, they're going to work out, right? So, like, I have to find these constant A and constant S, so that this equation, this differential equation, becomes equal to 0, okay? Now, to find that out, I'm just going to plug in this a e to the power of st into this differential equation, right? So for v divided by LC, I'm going to get a e to the power of st times divided by LC. Here I'm going to have the derivative and the second derivative, right? Now, if I take the common term out, which is a times e to the power of st, so from here to there, I'm going to get s squared plus s divided by rc plus 1 over lc equal to 0, right? So all I need to do now is to find out, well, solve this equation. It's not a differential equation anymore, it's just basically a polynomial equation. Now, for this expression to be 0, either a has to be 0 that cannot happen, because if a is 0, in a sense, I can say that, well, v is always 0. So I have chosen my v to be always 0. That cannot be true. Why? Well, this v is the expression of the voltage after time equal to 0. And I know for a fact that at least in the beginning, v is not 0. I have an initial voltage on the capacitor. So v cannot be 0, therefore a cannot be 0. Okay, how about e to the power of st? Well, that cannot be 0 either, because for that to happen, st has to be negative infinity. So for normal times, so for any kind of finite time, which is basically because I'm talking about t greater than 0, then I know that e to the power of st is going to be greater than 0, right? It's going to be a finite number. So then it means that I have to find the roots of this polynomial. I have to find what makes this expression equal to 0. So that's what I do. I bring this here, I write the big expression. We call this the characteristic equation of the circuit. Okay, so now to solve this, if you don't remember, here's how you solve here are the roots of a polynomial. So s1 and 2 are equal to negative b, which is b being, so for a s squared plus bs plus c equal to 0, we know that s1 and 2 are going to be negative b, so use capital B, plus minus root square of b squared minus 4ac. Or in some cases, people write negative b over 2 plus minus b over 2 squared minus ac. They're the same, okay? In this case, well, we're using this one, right? So this is basically the coefficient 1 over RC divided by 2. So that's negative b. This is b divided by 2 squared. And this is minus AC. So 1 over RLC times 1. Okay. So that's one. That's my S1 and that's my S2. So I just solve the characteristic equation. I found the S1 and S2. Remember when I decided that the answer to my differential equation has this form, I said that I have two constants, A and S, and I have to find those constants. I just found the answer to S. So I have two different answers for S, S1 and S2, right? For both of these answers, I know that if I put S1 equal to this expression into this form, no matter what is A, I'm going to get basically the differential equation equal to 0. Okay, that's why the S1 and S2 are important. And the other thing is to note that is that we found S1 and S2 based on the known values that are given to us by the question, right? So it's all based on L and R and C values that are given in the circuit, right? So I found the actual answer to my basically to the question that I had, that what is this constant value. So for this differential equation, we found these two answers for S1 and S2. So basically we found that V is going to be equal to A e to the power of st, and we just found what is the value for S, right? And we realized that no matter what is A, if I just basically place any of the S1 or S2 values instead of S, this differential equation is going to be valid. So now which one of them I should actually put in there, S1 or S2? Well, we can actually do both. We can say that V could be actually equal to a V1 plus a V2, where V1 is some A1 times e to the power of S1t, and V2 is A2 times the e to the power of S2t, right? So basically we are basically claiming that if I write my V based on the two of them, I can actually keep both of my roots, both of my answers, S1 and S2, of course with different coefficients, right? To prove that, you can simply take dv over dt for this V. So for dv over dt is going to be basically this expression. The second derivative is going to be this expression. If you plug that into differential equation here, you're going to get this expression. And if you, well, clean things up, move things around, you're going to get the expression that you can see here. And if you take the common term of a1 times e to the power of s1t and a2 e to the power of s2t, you will see that inside the parenthesis, we have expressions that we know they're equal to 0, right? Because, well, one of them is all based on s1, which we know that it's the root, it's the answer. We have already proven that. And one of them is based on s2, right? So the characteristic equation based on S1 and S2. So we can say that V is going to be equal to V1 plus V2. So that's basically it. All of these stuff here is just a proof that we can write V as V1 plus V2. So our solution to that differential equation in reality is not just A times e to the power of st. It's actually a1 times e to the power of s1t plus a2 times e to the power of s2t. We have s1 and s2. We still don't have a1 and a2. We know that this differential equation is going to be always valid for the s1 and s2 that we have, but, well, what should I choose for the a1 and a2? That's something that we're going to discuss in the future slides. So for the sake of cleanness, and since we're going to use this S1 and S2 a lot in our analysis, we're going to define some new parameters just to keep things a little bit simpler in writing, just because we're lazy and we want to write less, right? Think about it that way. So I'm going to define an alpha, which I'm going to call it the Neper frequency. And I'm going to define it alpha as 1 over 2 RC, and as is mentioned here. And I'm going to define an omega naught, which is basically the resonant radiant frequency, and I'm going to call it 1 over root square of, I'm going to define it as 1 over root square of LC. Okay, so if I define these two new parameters, then I can rewrite these equations for S1 and S2 as shown here, right? So it's going to be negative alpha plus minus root square of alpha squared minus omega naught squared. Okay, nothing is really happening here except for defining a couple of new parameters, alpha and omega naught. And these alpha and omega naught, we're going to use them to actually decide about certain behavior of the circuit, as we will discuss in the next slide. Okay. Just one thing you might want to actually note is that alpha is somehow related to R, and omega naught is related to LC. So alpha is really, you can say it's an indicator or it's a representative of how much energy is actually being consumed because there's an R in it, and omega naught is actually a representative or relation. Basically, it relates things to basically the inductor and capacitors combination. Okay, just keep that in mind for our future discussions. Okay, so now that I've defined S1 and S2 as this, and I've introduced alpha and omega naught, I can actually make an observation about these two roots. That observation is that these roots can actually have we could have three different situations for these roots, depending on the value of alpha and omega naught. What are those situations? Well, the first one is if alpha squared is greater than omega naught squared, right? Why this is important? Because, well, if this is true, then whatever is under this square root symbol is going to be basically a positive number, right? Therefore, both for this and that, for both of the cases, for both S1 and S2. Therefore, I'm going to have real and distinct roots. So by real, I mean it's a real number. I'm not going to have an imaginary number because I don't have to take the square root of a negative number. And by distinct, I mean S1 and S2 are going to be different from each other. Okay, we're going to call that situation an overdamped situation. In a few seconds or in a couple of minutes, when I'm actually discussing the right side of this slide, you're going to understand why we call this overdamped. The second situation is, well, of course, the opposite. So when omega naught squared is actually greater than alpha squared, then I have a negative number here. Square root of a negative number is going to be an imaginary number. So I'm going to have my roots S1 and 2 are going to be, well, negative alpha plus minus some basically k times I being equal to square root of -1, right? So it's going to be it's going to be a complex number, but the two roots are going to be complex conjugate, meaning that they have the same real part, but their imaginary parts are the opposite of each other, right? Let me actually write that here. So S1 and 2 are going to be equal to negative alpha plus minus I times k. This is basically k is representing square root of alpha squared minus omega naught squared, because omega naught is greater than alpha. Omega naught squared minus alpha squared, right? Because, well, this is a positive number. And then we have I as square root of negative 1, okay? That's why we call them complex conjugate. And then the third situation is simply when they're equal to each other, right? Then if they're equal to each other, what happens is that under the square root, things become 0. So this goes away. So S1 and S2 is just going to be alpha. So I'm going to have a real and equal roots, which is just negative alpha. Okay? Now, the first case, we called it overdamped. The second case, we called it underdamped. And the third case, we called it critically damped. So what is this? What's the deal with this damping thing? What is overdamped, underdamped, or critically damped? Or in some sense, undamped, right? So we have 4 different situations, and we're going to talk about all of them. First, imagine that I have a simple capacitor and a simple inductor in parallel with each other. There's no resistor. By definition, from chapter 6, we know that inductors and capacitors are elements that they don't generate or dissipate energy. So if I have an initial condition, an initial energy stored in this circuit just before I switch it out, let's say there was a source here, I stored energy into this circuit, and at t equal to 0, I opened this switch, right? So I just have the capacitor and the inductor, right? So what do you think is going to happen? And imagine that these two are actually ideal, right? So what happens is that this energy is in the capacitor. It cannot consume it. The only thing that could happen is that the voltage across, the energy across the capacitor could be basically translated into voltage. That voltage is going to cause a current. The current is going to flow through the inductor, so now I have some energy in the inductor. That energy in the inductor is in the form of a current, and then it's going to basically create a voltage across the capacitor. Now I have the energy in the capacitor. So if you think about it, what happens is that the energy is actually goes back and forth between the capacitor and the inductor. And that's what we call resonance. You might actually remember this from the physics, right? So the entire energy is in the capacitor for at 1 second, at one moment of time, and gradually this energy is actually shifted all the way to the inductor, and at some point all the energy is in the inductor, and then again the energy goes back to the capacitor, and this process continues forever, right? Because these two are ideal, there's no consumption of the energy, so this energy doesn't go away, right? So now that is the situation that I'm going to call it undamped. So if I look at in that situation, if I look at the voltage of the capacitor or the current of the inductor or the current of the capacitor, any voltage or current, any variable in this circuit, because the energy is going back and forth, but it never actually get reduced or like it increased, I can imagine that the value of that current or voltage that I'm interested in is just going to go up and down in a periodic way, right? Something like this pink curve, right? So I'm going to call that situation undamped. Why? Because I'm not damping the magnitude of any of that variable, right? Let it be the energy stored in the capacitor or the inductor, or the current or voltage of any of the elements. It's just going to go up and down, but it never, like the peak to peak value, it never reduces, right? So that is what I'm going to call undamped. So not damped at all, right? Now imagine that I add a resistor to the picture. Now every time that the energy of the capacitor is going to go to the inductor, some part of it, like if you think about it as a current, some part of this current is going to go to the inductor, and some part of it is going to go to the resistor. How much of it? Well, depends on the value of the resistor, right? The greater the resistor they have, like if the resistance is high, well, smaller current. If the resistance is actually small, a higher current, right? But some of it is going to go to the resistor, right? So you can think of it that if I actually start from the same point here, what happens is that every time I do a cycle, I might actually, the next peak is going to be a little bit smaller, and then a little bit smaller, 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 until I get to the zero, right? If I want to show it basically in a different axis so that you can actually see it and it's not confused with any of those curves, something like this. Imagine that I start from here, and little by little, it just goes to zero. We call this situation underdamped. So it is damped, but it's what we call underdamped because it's weakly damped. It's not strongly damped. So I'm going to call this underdamped, right? And then you can imagine that if I increase the size of this resistor, because, well, you can imagine that this going back and forth is really related to the frequency of the sinusoidal that I have here is related to the value of L and C, right? And we're going to call that, remember that we defined this omega naught as the resonance frequency, right? And this is the reason. So basically, it's related to L and C. And basically the frequency of this, like basically energy going back and forth between the between the inductor and capacitor, depends on the value of L and the value of C, right? But then at what rate this curve is actually dying out, it's actually exponential kind of a behavior. We're going to do the math and we're going to find that exponential. But at what rate it dies off, it really relates to the size of that capacitor, because that is what is dissipating, that is what causing the loss of power, loss of energy, consuming energy, right? So the higher resistance that I have, the basically, if I have a higher resistance, I'm going to have a stronger decay in the sinusoidal, right? So if this is a decaying sinusoidal, it could actually be like the one that I showed here, or I could have something like this, that it just dies out very quickly, or even something like this, right? So this dying out, and this blue curve that you see here is an example of an underdamped that dies very quickly, right? So this depends on how fast it dies out. It depends on the resistance and this alpha, right? So this alpha really kind of represents how strongly we're going to damp our behavior. And the omega naught is just representing what is the frequency of oscillations, right? That's why when alpha becomes much greater than omega naught, I'm going to say that it's overdamped. So if you continue this behavior that I was just explaining, at some point, instead of actually oscillating, like basically this is an underdamped still, but then at some point you might get to a situation that you don't oscillate anymore. It just dies down in the first cycle. We're going to call that a critically damped situation, where omega naught and alpha become equal to each other, right? And then, so that's the green curve here is critically damped, and the red curve is overdamped. Okay, so depending on the value of alpha and the value of omega naught, we could have any of these behaviors. So in terms of mathematics, the behavior is going to depending on the alpha and omega naught value, I might have real and distinct roots for overdamped situation. I might have complex conjugate roots for the underdamped situation, or I might have real and equal roots for the critically damped situation. In terms of the circuit behavior, I know that when I have an overdamped situation, I have this red trace where my basically the voltage or current or whatever variable that I'm looking at, it basically dies down without actually oscillating. With the critically damped, when I have omega naught and alpha are equal to each other, I have critically damped, which the behavior is very similar to the overdamped, but it's just at the edge of being underdamped, at the edge of oscillating. With underdamped, we are oscillating and dying, so I have a decaying sinusoidal kind of function. And then when it's undamped, which means that whenever, well, I have no resistor, so like this parallel resistor, if I make this infinity, sorry, if I don't have this resistance, then what happens is that if I remove this, it's almost like as if I made R infinity, right? So if R is infinity, then this resistance, I'm gonna have an open circuit here, right? And if R is infinity, this alpha becomes equal to 0. So when I have no alpha, no basically loss factor, basically alpha is representing the loss of energy, then I'm just going to be left with a capacitor and inductor, ideally passing the energy back and forth between them, so I have an undamped situation. Okay, so this is a lot to take in, I understand. Part of the intuitive part of the explanation, the behavior of the circuit, is something for you to actually have a nice internalized image for yourself about like what does overdamp and underdamp and critically damp means. But in terms of like the circuit analysis, what we care about is basically the math part of it. So the roots, the type of roots that we're going to have, is it going to be real roots or the complex conjugate roots, or like basically real and equal roots? That's the situation. If you're more interested in damping and the behavior and what does the overdamped and underdamped means, damping is something that is not only basically a concept in circuits. It actually is a physics concept. So there's a very nice video that I've put the link down here that you can watch. It's just, I think it's a few minutes, but it's a nice physical experiment that tells you that very clearly explains the concept of damping and what is overdamped, underdamped, and critically damped. Okay, so let's go back to our original question. So we started with this circuit. We wanted to find out what is the expression for V for t greater than 0. We did write the KCL. We found the differential equation. We found out that the solution to the differential equation is in this form: a1 e to the power of s1t plus a2 e to the power of s2t, right? Now, why did we discuss so much about this S1 and S2, and if basically what kind of roots we're going to have? Well, depending on if S1 and S2 are real distinct values, or they're equal but real numbers, or they're complex numbers, we're going to have different situations in terms of this expression. So let's actually consider these situations one by one. Okay, so now I'm going to first talk about overdamped case. So this is the case where I know that S1 and S2 are real and distinct values. Okay, so S1 and S2 are real numbers, positive or negative. There's no imaginary part in it, right? And that's very important for us in the sense that, like in the steps that we do here, and then in the couple of slides from now, you're going to see what happens if I have them as an imaginary number. Okay, so the solution is V equal to this, and we have S1 and S2. And if you remember, S1 and S2, we had them based on values of R and L and C. So everything is known except for A1 and A2, and we wanted to find these two coefficients. How do I find them? Because, well, no matter what is their value, the differential equation is still valid. So I cannot find them from the differential equation. Where do I find them? Well, initial conditions. So if you think about it, this is the voltage across these two terminals. It should be valid for all times, including time equal to 0. So at t equal to 0, this voltage should still be equal to the real voltage that is actually across these elements. So at t equal to 0, I know that V at 0 is equal to V0. What is V0? The initial voltage across the capacitor, as we defined, right? So from the circuit, so this is from circuit. So I just looked at the circuit and I made this observation. However, on the other side, from the equation or from the V expression, I know that, well, I can actually put t equal to 0 and I find v at 0. So v at 0, and I'm talking about 0 plus, right? And this is also 0 plus, right after the switching happened, is basically, well, e to the power of 0 is 1 for both of these terms. So I'm just going to get a1 plus a2, right? Therefore, I can say that a1 plus a2 is going to be equal to v naught, right? V naught is given. V naught is a given number. It's the initial voltage on the capacitor. So this is all either given to us by the circuit, by the question, or if you remember from chapter 7, we could actually find this V naught by analyzing the circuit before the switching, right? And find out what was the voltage across this capacitor just before the switching. So that would be the V at 0 minus. Then we would have said, because the voltage across the capacitor is a continuous parameter, it's one of our golden parameters, then I can say that V at 0 plus is also that, right? But at the end of the day, we are assuming that we know what is the initial voltage on the capacitor somehow, either by circuit analysis or it's given to us. So now I have one equation but two unknowns, right? A1 and A2 are my unknowns, and V naught is basically the known value, but this is not enough to actually find A1 and A2. How do I find A1 and A2? Well, the way I find it is to look at the initial value of the derivative. I know that if I take the derivative of this equation, I'm going to get S1 A1. So let me actually write it completely. So dV over dt is going to be A1 S1 e to the power of S1t plus A2 S2 e to the power of S2t. So if I make t equal to 0, I'm going to get this expression. E to the power of 0 is 1, so I'm going to get S1 A1, S2 A2. So here I'm going to write from the dV over dt expression, I have dV over dt at 0 plus equal to S1 A1 plus S2 A2. Good. S1 and S2 are known. We have already calculated them in the previous slides based on the values of R, L, and C. A1 and A2 are unknown, are unknowns, and the question is that what should I put on the other side of the equation? What do I get? So here I got, for the first side, for the first part, I got A1 plus A2 from the expression, and I got V naught from the circuit, so I made them equal to each other. So now from expression, I got this. What do I get from circuit? How do I find dV over dt at 0 plus from the circuit? Because it's not a voltage or a current that I would tell, well, I'm going to find that voltage or current at t equal to 0 plus. It's actually the derivative. Is there any way that I can find it? Well, I do, and it requires a little bit of observation from the circuit. So if you look at the circuit, or if you actually look at the expression, it's a dV over dt. Well, if you think about it, it reminds us of the current of a capacitor. We know that IC is C dV over dt, right? So I can say that dV over dt is really equal to IC divided by C. C is given. How about IC? So if I want, if I want this, if I want dV over dt at 0 plus, I need to find IC at 0 plus over C, right? C is given. All I need is the initial current of the capacitor. But is that something that is easy? as initial voltage of a capacitor? No. Why? Because initial current of a capacitor or the current of a capacitor is not one of my golden parameters. So it's generally not given. If you remember from the slide number 1, the initial voltage of the capacitor V0 was given, and the initial current of the inductor I0 was given. Initial current of the capacitor was not given simply because that's not one of the golden parameters. So what do? Well, let me see if I can actually convert this to one of the golden parameters, or both of them somehow. What is IC? IC, if I write the KCL, so KCL tells me IC plus IR plus IL is equal to 0. Therefore, IC is equal to negative IR minus IL. Now, what is IR? Well, it's actually V divided by R. So it's going to be, it's going to be negative V over R. And what about IL? Well, it's just IL. Now, if I want IC at 0 plus, I can say that this is V at 0 plus, and I know what is voltage at time 0 because that's the initial voltage of the capacitor. V is V. The voltage across this node and this node is the voltage across the capacitor. So this is going to be really negative V0 over R, which is a known value. And how about the initial current of the inductor? Great. I fortunately have that. So this is going to be I0, right? So I somehow could relate the initial current of the capacitor to my golden parameters, to voltage of the capacitor and the current of the inductor. And since I know the values of those parameters at 0 plus, I actually have my initial current of the capacitor at 0 plus, right? Therefore, so this is, I can say from here, so let's call this 2, and let's call this one 1. So 1 and 2 tell me that dV over dt at 0 plus is going to be equal to 1 over C times minus V0 over R minus I0. Okay, so this is basically now from, let's call this 3 and this 4. 3 and 4 will tell me that S1 A1 plus S2 A2 is going to be equal to 1 over C negative V0 over R minus I0. And now I have two equations and two unknowns. So this is the equation number 1, and this is equation number 2. So I'm going to call this EQ1, and this is EQ2. Now, using these two equations, I can actually find A1 and A2, because everything else other than A1 and A2 in these two equations are known. So everything else is basically S1 and S2 that I have already calculated, R, C, and L that I already have them, and V0 and I0, which are the initial conditions, which they are already given to me by the question, or I can calculate them on my own. Okay, so once I have A1 and A2, I'm done. So I have found my expression. So this was a long way, and it might be actually, it might look a little bit intimidating. It might sound very complicated, but if you think about it, most of the stuff that we did here was just the proof, right? To find like basically how, like the proof of how do I find S1, S2, A1, and A2. Now that we have their expression, we can always use these expressions in solving examples. Whenever you solve a parallel RLC circuit, you know that S1 and S2 are just going to be those expressions that are based on R and L and C, right? And you know that A1 and A2 are going to be found based on this two equation, two unknown. You don't actually have to write a single KCL or KVL if the circuit is actually simplified to this form of parallel RLC, right? You just write A1 plus A2 is equal to the initial voltage of the capacitance, and then you find S1 and S2 from those expressions, and then write S1A1 plus S2A2 is equal to 1 over C, which is given, plus times this expression, which is also all given parameters. Okay, we're going to do an example of this so that you can see how simple things are. Okay, so let's do an example. We have a parallel RLC circuit and we want to find the expression for V. We know that from our discussions up to now, we know that V is going to have a form of A1 e to the power of S1t plus A2 e to the power of S2t. But well, our job is to find A1, S1, A2, and S2. Once we have them, we're done. Okay. Since we only know how to solve overdamped situation, it would be nice. This example better be overdamped, but it would be nice to actually check the damping situation and make sure that it is overdamped based on the conditions that we had for damping situations. So first we calculate alpha and omega naught. So alpha, I know that it's equal to 1 over 2 RC, and omega naught is equal to root square of 1 over LC. Okay, so alpha is going to be equal to 1 over 2 times R being 200 and C being 0.2 microfarad. So 0.2 times 10 to the negative 6. So this is going to be equal to, I bring the 10 to the 6 up here, and 2 times 0.2 is 0.4 times 200, I'm going to have an 80. So 100 over 80 is 1.25, and the rest is going to be 10 to the 4. So that's my alpha. Now, what's the omega naught? Well, actually, I care about omega naught squared, so it's going to be basically, let's just write that down. So omega naught squared, because I compare, if you remember from the conditions, I compare omega naught squared with alpha squared. So omega naught squared is going to be 1 over LC. It's going to be equal to 1 over 50 times 10 to the power of negative 3, that's 50 millihenry, times 0.2 times 10 to the negative 0.6, that's my 0.2 microfarad. So this is going to be equal to 10 to the power of 9, and 50 times 0.2 is 10, so it's going to be 10 to the power of 8. Now, what would be the alpha squared? Because I have to compare alpha squared with omega naught squared. Alpha squared is going to be 1.25 times 10 to the power of 4 squared, right? So that's going to be equal to 1.5625 times 10 to the power of 8. Okay. Now from these two expressions, I can say that since alpha squared is greater than omega naught squared, therefore we have an overdamped situation. Now, first thing first, I have to find S1 and S2. I know that S1 is equal to negative alpha plus alpha squared minus omega naught squared under the radical. So it's going to be equal to negative 1.25 times 10 to the 4 plus root square of 1.5625 times 10 to the power of 8 minus omega naught squared, which is just 10 to the power of 8. So this is going to be equal to, well, this is negative 12,500, and plus this is basically 0.5625 times 10 to the power of 8. That's root square of 10 to the power of 8 is just 10 to the power of 4, and root square of 0.5625 is 0.75. So I'm going to get negative 12,500 plus 7,500. which is going to be equal to negative 5,000. That's my S1. I found my S1. S2 is just going to be negative alpha minus this root squared. So alpha squared minus omega naught squared. So this is going to be equal to negative 12,500 minus 7,500. So I'm going to get negative 20,000. Great. So I found my S1 and S2. All I need is A1 and A2. So for A1, and A2, I know that I have to solve those two equations, two unknowns, right? For one equation, for one of them is A1 plus A2 is equal to V0. So what is the initial voltage on the capacitor? It's actually given. It's 12 volts. So I know that A1 plus A2 is going to be 12 volts. What is the second equation? Well, I know that S1A1 plus S2A2 should be equal to, and we got from the previous slide that this should be equal to 1 over C times minus V0 over R minus I0. Okay, so what is this? This is 1 over 0.2 times 10 to the negative 6. V0 is 12, so minus 12 over 200. And I0 is this guy, 30 milliamp. So minus 30 times 10 to the negative 3, or I can just bring it here. So 30 over 1000, right? 30 milli. Common denominator of the two, I get, so I bring the 10 to the power of 6 up here over 0.2, and then here I can take the common denominator. It's going to be negative 12 times 5, so negative 60, and negative 30, so negative 90. So I'm going to get negative 90 divided by 0.2, that's going to be negative 90 times 5, so negative 450. And 10 to the power of 6 over 1000, I'm going to get a 10 to the power of 3. So times 10 to the power of 3. Okay, so basically S1 was negative 5,000 times A1 plus S2, which is negative 20,000 times A2 should be equal to negative 450 times, well, negative 450,000. Okay, so I have equation number 1 and equation number 2. Once you solve these two, you're going to find your A1 and A2. So if we do the math, you find A1 to be equal to negative 14 and A2 equal to 26. Okay, so now I have everything. I have A1, A2, S1, and S2. So I can write my voltage expression, Vt, to be equal to negative 14 e to the power of S1 t, so negative 5,000 t, plus 26, which is A2, times e to the power of negative 20,000 t. And that's in volts. And basically for t greater than or equal to 0. So as mentioned before, and as I promised, although the explanation of why we're doing all of this was actually quite complicated, it might take some time for you to actually take it in. The procedure to solve RLC circuits is actually quite formulated and quite easy. All you need to do is, well, the first step would be calculating alpha and omega naught, making sure of the damping situation. In this case, it was overdamped. Now that we know it is overdamped, then we're going to use the S1 and S2. We have the expressions, so we just plug in the numbers for alpha and omega naught, and we find the numbers for S1 and S2. Once we have the numbers for S1 and S2, we write the two equations, two unknowns based on the initial conditions, and we find A1 and A2. And once we have these four parameters, we have the expression for the voltage of across the three elements. Now, if the question is asking you not to find V, if they're asking you, for example, find the current of the capacitor, right? Again, you don't go and find the current of the capacitor directly. You find the V, and then you say that, so if the question asked for, let's say, IC, then I know that IC is equal to C dV over dt. So once I have the expression for V, I just take the derivative of that expression, multiply it by C, and now I have the current of my capacitor, right? If I wanted to express the current of the inductor, it would be the integral of V plus the initial current, which it is already given by the question. If I wanted the current of the resistor, it would be just V divided by R. So it would be the same expression divided by 200. Okay, so you can see that once you have the V, you pretty much have everything in this circuit. That's why I'm saying always go with the V for a parallel circuit, and then you realize, and we'll see later, for a series circuit we always find I, because for 3 elements that are in series, the common variable is their current. Okay, things might actually get a little bit more complicated. This is the simplest form of an RLC circuit. Think about it like you might actually have instead of one resistor, you might have a few resistors. So you might, you can actually combine them into one resistor. That's not really a different kind of a circuit. You just need to do something before actually doing all this stuff that I discussed in this slide, right? So it's just basically a matter of doing some analysis before getting into this. The other way that things might get complicated is that this initial condition for the voltage of the capacitor or the current of the inductor might not be given to you, and you might actually have to find them yourself, the same way that we did for RL and RC circuits. If the switch was shown and the rest of the circuit was shown, you would just basically go back and look at how the circuit looks like before the switching, find the initial condition, and then do all the stuff that I described in this slide. Okay, so this was for the overdamped situation. In the future slides, we're going to be talking about how to solve, how the solution is going to be different for the underdamped and the critically damped situation, and that is when we're done with natural response of parallel RLC. Then we have to talk about the step response, and then we have to talk about the same stuff for the series circuits.